Section 5, we're going to look at isotopes and atomic mass. And this will get into explaining why the mass number doesn't exactly match the mass of the element that's frequently written on the periodic table. We'll also get to see a couple different notations for how the different isotopes can be written to emphasize this. So, isotopes are atoms of the same element, which means, of course, that they have the same number of protons, but have different mass numbers. And if they have different mass numbers, then as I just mentioned, same number of protons, but different number of neutrons. So this here is magnesium ribbon, fun metal to play with. It's flammable and burns incredibly bright white. Sparklers used to be made out of magnesium. Any of your bright white fireworks are usually magnesium or a magnesium aluminum alloy in there. But anyway, they have shaded here. Not that there'd be any difference between the atoms, and again, not that we can actually see them or they have color, but they have shaded them to show that there are different isotopes, different versions of magnesium that exist. And on top here, we have the mass number. We have a symbol there, and on the bottom we have the atomic number. Now, I have seen these written without the atomic number down low. It's certainly easier if it's done, but if it's not there, you can just go look it up on the periodic table. I particularly like this notation because then you have the subtraction problem set up for you already to figure out your number of neutrons. In fact, we'll just do that here real quick. We'll subtract out 12 from all of those, and this one has 12 neutrons, this one has 13 neutrons, and this one has 14 neutrons. And so those would all be different versions of magnesium, different isotopes. So as I said, this symbol here then just does that, and this one's written a little bit nicer than what my handwriting was, so take a moment and jot it down, but we've kind of already explained everything there, so I'm going to move right along. Here's some more examples, and so here we have oxygen, phosphorus, and zinc, and you'll notice that we have the atomic number and number of electrons match the bottom number, and that the number of neutrons is, again, of course, just a calculation where we subtract out those two to get our number of neutrons row there. 3 naturally occurring isotopes of carbon, so we have carbon-12, carbon-13, and carbon-14. Now, I will say most often when I've seen this, we have actually both notations here. One is that, and the other is this. Most often when I've seen the notation I've boxed in there, it'll be spelled out, carbon-12, carbon-13, carbon-14, and then this notation will use the superscript before the symbol to give you your mass numbers, and just use the symbol instead. Again, I have seen it C12. Most often I've seen it as the 12C, 13C, 14C like this, or the name spelled out if you're going to do the hyphen version. I like this notation better, as I mentioned, because this one has the subtraction problem set up for you as soon as you look up the atomic number. So the atomic number for this one is 6. And so then you've got the subtraction problem set up there to come up with your number of neutrons. So 12 minus 6 is 6 neutrons, 13 minus 6 is 7 neutrons, and 14 minus 6 is 8 neutrons. And then your number of protons and electrons are just the atomic number. And just to be clear here, number of protons, number of electrons, these two columns here match the atomic number down low, whereas your number of neutrons come from the subtraction problem between mass and the number of protons to give you number of neutrons. Those numbers are not the number of neutrons. Again, it's the subtraction problem set up for you. So here we're asked to do the symbols. So we have 8 protons, electrons, so we know that's our number down there low. To get the mass number, we have to add the protons to the neutrons, which gives us 16, so that becomes our mass number up here. And then we have to go look up what atomic number 8 is, and you'll find out that that's oxygen. Here we'll do that addition, so that will give us 37. You go look up the atomic number 17, you'll find out it's chlorine, and so chlorine 3717. And this one here, we add those two together and we get 107, and you go look up atomic number 47 and you'll find out that it is silver, and the mass number is 107 there. So looking at these, X is just a fictitious chemical symbol here, but it says which are pairs of isotopes with the same element. Well, if it's the same element, it's got to have the same number of protons, which means the same atomic number. And so then looking through here, that would be B. and both of those would be carbon. And we got carbon 12 and carbon 14, which we saw a moment ago. And then this one here says, which pairs do both atoms have 8 neutrons? So that means our subtraction problem has to come out to be 8. So if we do this subtraction problem, that's 7 and 8. So not that one. We do this subtraction problem. We did it just a moment ago, but that's 6 and 8. We do this one here. Hopefully it's 8 and 8 because we only have the one choice left, but sure enough it is. And so C has that. And I'll leave it up to you to take a moment and go look up each of these elements here. I'll point out that the second choice on A is the same as the first choice on C, so you really wouldn't need to go look it up, but it's good practice. So now we're getting into the atomic mass, and the atomic mass is what's on the periodic table rather than the mass numbers. And you'll notice that the atomic mass is not a whole number. All of our mass numbers have been. The reason for this is because this is a weighted average of all of the naturally occurring isotopes. That is, there's different versions of them. For example, carbon, if you go look it up on the periodic table, is 12.01 for its mass. And we mentioned just a moment ago that there's carbon 12, carbon 13, and carbon 14. Well, if you average those three numbers, you just do 12 plus 13 plus 14, because you know when you take an average, you just add all the numbers together and then divide by how many there are, 3, you'll find out that the average there is 13. So then you think, oh, well, maybe it should be just 13 down here for the atomic mass, but it is a weighted average. So it turns out that there's actually about 99% is carbon 12 and about 1% is carbon 13. You'll say, wait, those add up to 100. What's going on here? Well, these are rounded to the nearest whole number, and this one here, it's called a trace amount. I think there's less than 0.001%, maybe even less than that. And so really what we have to do is we have to add 12 99 times. And then add in 113 there. Or we can take the shortcut, and instead of adding a lot of times, we can multiply. So it turns out that if you take 12 times 99, and then you add on to that 13 times 1, and then we ignore the 14 because it's so tiny, and then we divide by the number that we have there. Well, I did 99 and 1 for my percentages, so that'd be 100 of them there. You find out that that comes out to be 12.01. Exactly, in fact. And that's this one here. And again, it's based off of comparing everything to carbon 12, that our mass number comes from carbon 12, and so then we get a average atomic mass on the periodic table. But that average is based off of how common each version is on Earth. So here you're just asked to look up the atomic mass of each element. So you go to the periodic table, and that's 40.08, 26.98, 207.2, 137.3, and 55.85. Will tell you I know a lot of the masses on the periodic table, especially of common elements, at least to the ones place. There's a surprising number that I've managed to memorize, but there's definitely some here where I was looking at my answer key that I have on the screen here just to help me out. You'll have a periodic table. It's as simple as looking it up. Now, it turns out that when you have more than one isotope, and there are some elements that have only one isotope, and therefore their atomic number matches their mass number. When that's not the case, if we look at the mass number, as I just did a moment ago with the carbon 12 there, well, it has a mass of 12.01. That means that the carbon 12 version is the most common version of it. The symbol whose mass number is closest to the average atomic mass is your most abundant isotope usually. There are a few exceptions. You're not going to be asked any of those, it's weird when we get into the man-mades, because since they're not common, then there's not an abundance of them. They're man-made. And so then what we end up having to do is distinguish between each of them individually, and then on the periodic table, we use a mass number like that, and we do it for the most stable version instead. Again, there are a few exceptions to this, especially on elements that have lots of different versions. 10, the element Sn, actually has 10, the number 10, different isotopes. I believe it has the most naturally occurring isotopes of any non-man-made element. And there are some where they don't match. I became curious one time, and I'm the kind of nerd who went and looked it up and found the handful where they don't match. It kind of surprised me how many they were, but a good rule of thumb is that the atomic mass probably matches the most common isotope, the most common mass number. This table then goes back through those magnesiums that we started out with. We're looking at the different isotopes here, and you can see all of the different ways of listing it, the two different symbols here. You can see that the protons are all the same, the electrons are all the same, the mass numbers are different, and that causes our number of neutrons to be different because it's a subtraction problem there, and we did that one earlier. And then here they have the percentages. Well, when you have the percent abundance, what you can do is you can imagine you have 100 atoms of them, and if you had 100 atoms of them, then 78.7 would have a mass of 24. Now, it's not possible to have 0.7 of an atom. That's okay. If you imagined you had 1,000 or 10,000, then these numbers become realistic, unless you want to go out to more decimal places, but this is good enough. And so we do those, and then we've got 10.13 times 25, and then we have 11.17 times 26, and then we just punch that into a calculator, and you will find that when you do that, you get 24.31 AMU. And that is the mass, the atomic mass that is on the periodic table, the average atomic mass. Now, a lot of times, because this is an average, I'll have students say, wait a second, I added 3 things there, I need to divide by 3 still. I suppose the 2 disclaimers I have to that. One is the weighted average. These percentages take care of that division process for you, essentially. Reason number 2 is averages always have to be between the minimum and the maximum value. So your final answer on this one should be between 24 and 26. You can't have an average that is outside your min and max value. So 24.3 is, if you divide that by 3, it's 8.1 something. That's way outside of this. That can't be right. So this one here is it. And that's as straightforward as it is. And then they just have a graph here that shows kind of the same thing based off of how common they are. But the 3 of them together are what give us the average atomic mass on the periodic table. This talks through doing what I just did. I will point out I just noticed a typo here on this one, that C should be there for the chlorine 35, which is the same as that one there. And they're simply pointing out here that because the mass is this, that the chlorine 35 has to be more common than the other version of chlorine, the chlorine 37. And so then that's why. And I've walked through how to do the calculation, but I'll show it to you again here. We simply do the mass number times by the abundance, 75.76. And the mass number times by the abundance, 24.24. Now, backing up, I realized I made a small mistake on the last slide. I said you don't have to do division. If you treat these as decimal percentages, 0.7576, you don't have to do division. What I actually did last time, and I just did it without even thinking, is once I was done doing that, since I have 100 of them here, 100%, you do have to divide that by 100 for your weighted average. And when you do that, you will get 35.45. So apologize for that. Hopefully it makes sense here. You can either turn your percentages into decimal percentages, or you can leave them as percentages and divide by 100 at the end. Don't do both, or you'll end up with a number that is outside of that. This here then just talks through it, and this one here then asks which is more common. Well, if we have 6.9, then lithium-7 has to be more common than lithium-6. And if you back up a few slides, you rewind a little bit, you'll see that that was actually on the table as one of their examples. There is a way to actually go about solving for what the abundances are based off of this. If you have me live, I'll show it, but it's not something that I'm going to test you over. Getting into this one here, we have potassium in the form of 39, 40, and 41. If the mass on the periodic table is 39, then the 39 one has to be more common. I'll leave it as a challenge to you on these two here. To figure out your number of neutrons and other subatomic particles, it's good practice, as well as writing the symbols with the superscript and subscript number before the symbol. Anyway, that finishes up section 5.